So in this video lecture we'll be starting with the work energy method, and the basis of this work energy method again lies in the D'Alembert's principle itself, that is summation of F minus ma is equal to 0. So we can take summation of F equals to ma. Now here what we do is let us take an object which has this summation of forces acting on it, and there is a motion due to this, and let us say that u is the initial velocity, and after some time t, let us say that this object has a displacement of s and it attains a final velocity of v. Okay, so we can say that a is equal to v square minus u square upon 2s, right? And what I'll do is I'll take this s on the other side, on the left hand side. So I'll get summation of f into s is equal to half into m into v square minus u square, right? So this term which is there, this is force into your displacement. Force into your displacement is nothing but the work, right? And the units are Newton meters, or the units of force and the units of displacement. And on the right hand side what you see is half mv square minus half mu square. So this is nothing but the final kinetic energy minus the initial kinetic energy, and hence this is called as the work energy method. Okay, so work done is equal to final kinetic energy minus initial kinetic energy. So this work done, which is F into S, if I have a graph with me where let us say your force is a function of displacement, then the area under that curve will be the work done. Okay, and to get the area under the curve, we would simply integrate it with, let's say, the strip having a width of ds. So f into ds, integration from s1 to s2, will give you the total work done, that is the area under this curve. Okay, and there is one note that since normal reaction is always perpendicular to the displacement, the work done by it is 0. For example, if there is an object like this is the force that is acting. Okay, and let us say after some time it reaches to this position, so it has traversed a distance of s. So the work done is F into S, right? F into S is the work done. But the normal force, of course, this object, since it is resting on the ground, it is also going to have a normal force. What is the work done by this normal force? There is no displacement in the vertical direction. That is the reason that the normal reaction is always perpendicular to the displacement, and hence the work done by the normal reaction is always going to be 0. So now we will see work done by a resistance, and in this case spring is one of the most important ones that we will be studying. There are different types of resistance. A resistance is something that is going to always do opposite work of what is being done. So if I am trying to push this object inside in this direction, the spring is going to do an opposite work of pushing it back to the opposite direction, right? So there are different types of resistance. For example, this is one of the examples. This is in the harbors where the ships are docked. So when the ship is trying to get docked in the harbor, we have these impact absorbers which are there. So when the ship collides with it, these impact absorbers, they absorb that impact of the ship, or basically this impact absorbers are doing a work opposite to that of the ship. So the ship is doing a work of, in this direction if it is going, then let us say F into S is the work that is being done in this direction. This impact absorber will do a work in the opposite direction. So let us come to the spring again, which is a very important resistance. A spring is generally represented by its stiffness, which is denoted by this letter K. A stiffness is nothing but it is the force required to produce a unit deflection. Okay, so this K is nothing but force per unit deflection. Okay, and generally the units of stiffness are given as Newton per meter. So in a very simple case, if the spring is having a stiffness of 5000 newtons per meter, what this basically means is that for that spring to be compressed by 1 meter, I need 5000 newtons of force. Okay, so if I apply 5000 newton of force to that spring, the spring will get compressed by 1 meter. Okay, so how much force is that spring giving me if there is a spring like this? So this simply means is that if I am applying a force of 5000 newtons, there would be a 1 meter of deflection, right? And after 1 meter of deflection, I cannot further deflect the spring. So how much is the resistance force that is given by the spring at that point after the deflection of 1 meter, after it has been deflected to 1 meter? The resistance force that is given by the spring is called as Fr, and that will also be equal to 5000 newtons. Okay, so I am applying here a force of 5000 newton. I am deflecting the spring, or I am pushing the spring by 1 meter, and after that the spring also has to give me a equal and opposite reaction of 5000 newton. This is the resistance force that is given by the spring. Okay, in general terms, if I am saying, if I want to find this resistance force for a deflection of s meters, okay, for a deflection of s meters, so how much will be this resistance force? For finding this resistance force, first I need to find how much force I need to apply to cause this s meter of deflection. So again, going by this definition of K is equal to force per deflection, it will be F per S. K is equal to F by S. So F is equal to K into S. So this is K into S is the force that I have to apply here to cause a deflection of S. And after that, this resistance force which it will give me is also equal to K into S, right? So that will also be equal to K into S. So we can generalize this and we can say that the force of resistance by spring Fr is equal to K into S. And the work done by a spring is always negative in nature, since the force developed in the spring is in opposite direction of the displacement. So as I showed you in the spring, when I was applying a force in this direction, the resistance force which was developed was in the opposite direction. I am applying a force like this and the displacement is also happening in this direction, but the resistance force is working in the opposite direction. Hence, the work done by a resistance is negative. We will take example of this here, and the case one which we are studying is when the spring is compressed. So here I have shown these two springs. The position 1 which is there, this is the unstretched position of the spring. Unstretched position means that in this case the spring is neither being elongated, neither the spring is being compressed. This is the unstretched position, and in this case S1 denotes that how much is the spring stretched. So obviously in unstretched position the spring is not stretched, therefore S1 will be equal to 0. Okay, for the unstretched position. Now what I am doing is I am applying a force here like this. I am trying to compress the spring. So when the spring gets compressed, it gets compressed by how much? This much distance, right? This much distance is what it has been compressed to. I would say that distance being S2. S2 is not equal to 0 and S1 is equal to 0. This is the stretched position. This is the unstretched position, right? This is the direction of the displacement, which is to the left. The direction of the force of resistance will be to the right, and hence the work done is negative. The equation for the work done by a resistance is given as WR is equal to minus of integration S1 to S2 Ks ds. This Ks is nothing but your Fr, right? And Fr into ds is nothing but your work done. Correct? So in this case, S1 is 0, this is equal to 0, this is not equal to 0, and this will always be a positive value. Okay, the displacement will always be a positive value. Yeah. So when you solve this, you will get a work done as negative. Work done by the resistance as negative. This was the case when the spring is compressed, okay, and when I was applying a force of F from this side. Now what I will do is that I will remove this force. If I remove that force, what will happen? The spring will try to retract back to its original position or to its unstretched position, right? If I remove the force, it will come back to its unstretched position. So what is the work done in that case? Let us see. So now we are at this position, okay? When we had applied the force, we are at this position now. This is the stretched position, okay, because I was applying a force. But now I am removing this force, and mind you, here now S1 is not equal to 0. This is position 1 of the spring, and position 2 will be after it has retracted back to its unstretched position. So this is the case 2 when the spring is released. And in this case, when the spring is released, the work done by spring is positive only when the spring force is in the direction of displacement. So see now what happens. After the spring gets released, it goes back to its unstretched position. So what is the direction of the displacement? The direction of the displacement is in this direction, and the force which is also in this right direction only, because it is pushing it in the right direction, correct? This is the stretched position, this is the unstretched position. S2 is equal to 0, S1 is not equal to 0. The equation in this case of the work done will also be the same, okay? Even though the work done by the spring is positive in this case, still the equation that we would be using is this only. Now why? Because you see that S1 is not equal to 0, S2 is equal to 0. So if you solve this, at the end what you will get is minus ks square by 2. So it is, at the end you will get ks1 square by 2, okay? So it's a positive work. Hence, the point that I want to make here is that the equation of the work done by the resistance will remain the same. What will change is only the limits. So in the previous case, when the spring was getting compressed, in that case, position 1 was the unstretched position, position 2 was the stretched position. Hence, in position 1, S1 was equal to 0, S2 was not equal to 0. Now, in this case, when the spring is released, position 1 is the stretched position, position 2 is the unstretched position, right? Case 3 is what happens when the spring gets elongated. Now this is the unstretched position, S1 is equal to 0, and this time I am applying a force in this direction. So what will happen? The spring will get elongated, S1 is 0, S2 is not equal to 0. This is the displacement that is happening, which is again a positive displacement, okay? And the direction of the displacement is in this direction. The direction of the resistive force is in the opposite direction. Hence the work done is negative, and it is given as WR is minus of integration S1 to S2 Ks into ds. That's it. So here S1 is equal to 0, S2 is not equal to 0, and it is positive. So let us start with the numerical. What is given is a 1500 Newton crate is pulled along the ground with a constant speed for a distance of 25 meters. Okay, so let us say that this is that crate which we are pulling using a cable that makes an angle of 15 degrees. So there is a cable like this, and it is making an angle of 15 degrees. Okay. Determine the tension in the cable and the work done by this force. The coefficient of kinetic friction between the ground and the crate is 0.55. So mu here is 0.55. Okay. Mu is 0.55, and the weight of the crate is also given, which is 1500 newtons. So 1500 newtons is the weight. Fine. So we have to solve it using work energy method. What is the work energy method? It is work done is equal to half m v square minus u square, that is change in the kinetic energy. So what is the work done? Work done is force, all the summation of forces acting along the direction of the displacement multiplied by the displacement. So if I do summation Fy equal to 0, now because since here the friction also has to be taken into consideration, therefore we need to find the normal reaction here. Let us say that N is the normal reaction, and since the movement is happening in this direction, the frictional force would be like this, which is 0.55 times N, right? If I do summation Fy equals to 0, what I'll get is 1500 is equal to N plus the sine component of this T, which is T sine 15. Okay, so N I will get as 1500 minus 0.2588 times T. The frictional force I would write here as F mu would be equal to 1500 multiplied by 0.55, which is 825 minus 0.1424 times T. This is your frictional force, F mu. Okay. Now, when we do summation Fx equals to 0, and for how much distance it is moving, it is moving, so it is moving at constant speed for a distance of 25 meters. So constant speed means v is equal to u, one thing is there, and s is equal to 25 meters. This thing also we can understand. Now summation of Fx, these are the forces causing motion, right? So we will get here as T cos 15 minus, this is summation Fx, is equal to T cos 15 minus 825 minus 0.1424 times T. When we solve this, we will get 1.1083 times T minus 825. So these are the forces which are causing the displacement. We need to multiply them with 25. So 1.1083 T minus 825 into 25. This is the work done. This is equal to half into the mass would be 1500 by 9.81 into v square minus u square. So now it is moving with constant speed, therefore v is equal to u. So you can say that v square minus v square or u square minus u square, and this term is going to get 0, right? So T you will get as 744.383 newtons. Okay, let us move on to the next numeric. So what is given is the smooth plug has a weight of 20 newtons. So this is having a weight of 20 newtons and is pushed against a series of Belleville spring washers, so that the compression in the spring is S is equal to 0.05 meters. If the force of the spring on the plug is F is equal to 3 into S raised to 1 by 3 newtons, where S is given in meters, determine the speed of the plug after it moves away from the spring. Neglect friction. So see, what is given is the weight of the plug is given 20 newtons. So mass would be 20 by 9.81 kg. Fine. These are your Belleville spring washers, and they are already compressed. Okay. So let me draw here. Now this is already a compressed state. Okay, so I'll say S1 is equal to 0.05 meters, right? And what I want is, now if I leave this block at this position. It means if I stop pushing it against the spring, if I just leave it, then obviously the spring will retract back to its original position, right? And this plug which is there, it will move away in this direction. So how much it moves away, or rather what is the speed of that plug after it has moved away, that is what we need to determine. So here S1 is 0.05 meters. When it is relaxed, right, it would look something like this, or rather, so this is the relaxed position or unstretched position, S2, which is equal to 0, right? And here instead of giving the stiffness of the spring, directly the resistive force is given, okay, which is 3s raised to 1 by 3 newtons. Therefore the work done by the resistance will be what? Work done by resistance is minus of integration of S1 to S2, the resistive force Fr multiplied by ds. This is the work done by the resistance, and Fr is already given, so it is minus of integration. S1 is 0.05, S2 is 0, 3s raised to 1 by 3 into ds. So let us see how much we get this work done. Wr is equal to minus of 3 into s raised to 4 by 3 upon 4 by 3, right, going from 0.05 to 0, and here you will get minus of 9 by 4 into, this would be 0 minus 0.05 raised to 4 by 3. So you will get this work as positive, which is 0.04144 Newton meters, right? So this is 0.04144 Newton meters, and there is no other work that is being done, because see, this pushing which we were doing of this plug, we are now removing that force. Okay, now the only force that is active in this scenario is the spring force, which is going to push this plug in this direction, right? So that is the only thing that is active, and we have got that work done as positive because the displacement is also happening along the resistive force of that spring. Therefore work done is equal to change in kinetic energy, I'll write delta Ke, okay, change in kinetic energy. So work done is 0.04144 is equal to half into 20 by 9.81 into v square, that is the velocity, final velocity. And see, since we are neglecting the friction, there is no frictional force like this, hence after the spring pushes this plug, there is nothing that is going to stop it, right? So the final velocity, we won't consider it to be 0. There is some final velocity. However, the initial velocity when the block is at this position like this, the initial velocity is 0, right? So initial velocity is going to be 0, and if you solve this, you will get V as 0.2016 meters per second. So let us solve the next numerical. What is given is the 1.5 kg block slides along a smooth plane and strikes a non-linear spring with a speed of V equals to 4 meters per second. The spring is termed non-linear because it has resistance of Fs is equal to Ks square, where K is 900 Newton per meter square. Determine the speed of the block after it has compressed the spring. S is equal to 0.2 meters. Now these springs are called as non-linear springs is because in a normal spring, if you plot the graph between the force and the displacement, it would be like if this is force and if this is displacement, then that graph would be a simple straight linear line, and if you take the slope of this would give you the stiffness of that spring. And these kinds of springs are generally, they are of equal pitch equal diameter. So means this diameter remains the same, this pitch between each of the turn, it remains the same. So such kind of springs are termed as linear springs. But in this case, what happens is generally it is seen that this bigger diameter which is there, it is and you can see the pitch is also greater. So this is easier to get compressed as compared to this one. Okay. So in this linear case, if for example 200 newtons per meter is the stiffness, so for 1 meter, if 200 newton is the force required, for 2 meters it will be 400 newtons, right? So it doubles the force also. But in this case, if it is for 1 meter, I need 200 newton of force. For 2 meters, it might not be 200 newtons, but it might be something like 800 newtons or 1000 newtons, like that. So the force also does not vary linearly. Okay. Anyways, that is also not of our concern right now. We have been given the stiffness and the resistance force which is there in the spring. We have to use that, and we need to determine the speed of the block after it has compressed the spring with 0.2 meters. So after it has compressed the spring with 0.2 meters, what is the speed of this block? Initially, the speed, I'll write u is equal to 4 meters per second. When this spring gets compressed by 0.2 meters, how much is v? Okay, so mass is 1.5 kg and u is 4 meters per second. Fr I will write, since here it is given as Fs, but I write it as Fr since that is our terminology. Fr is Ks square, where K is 900 newtons per meter, so I'll write just 900 S square. Okay. Work done by the resistance. Now at position 1, this is the position 1 when the spring is uncompressed or it is unstretched. S1 is equal to 0, S2 is equal to 0.2 meters, right? So it is negative of integration. S1 is 0, S2 is 0.2 into Fr into ds, which is 900 S square into ds. Okay, so it will give you minus 900 S cube by 3. So it is minus 300 S cube going from 0 to 0.2. 0.0 to 0.2. So this is going to give you WR is equal to minus 2.4 Newton meters. Now it is sliding over a smooth plane, hence there is no friction, no frictional force. And what else is the work done here? So in this case, there is no other work that is being done because there is no external force by which we are pushing this object, right? It is going or it is sliding along a smooth plane and we do not know what force was applied. So right now it is just sliding along the smooth plane and there is no external force being applied. So it will keep on sliding by its initial velocity of 4 meters per second with no other external force, right? So these are certain problems with certain idealistic conditions. These cannot be realistic conditions. So the work done will only be due to this resistance, which is minus 2.4. So work done is change in the kinetic energy. Therefore it's minus 2.4 is equal to half into m is 1.5, half into m v square, which is what we do not know, and u square is 4 square. Therefore, V will come out to be 3.5778 meters per second. So what is given in this question is a 2.7 kg block is released from rest at A and slides down the smooth parabolic surface. Determine the maximum compression of the spring. So the mass is given, which is 2.7 kg, and the stiffness of the spring is given. It is a linear spring. It is 876 Newton per meter. And and this equation of the parabola is given. Now you need to understand what forces are acting here. And see, this is a smooth parabolic surface, so there is no frictional force which is going to act, and the normal force which is there, as we know that normal force does not cause any work, so no work is done by the normal force. Hence the only force that we are concerned here is the downward acting weight or mass, 2.7 kg, which is acting here, right? And this is what is going to cause the motion, right? And what is the displacement in this direction? The only displacement in this direction is 0.6, because when block at point A reaches the point B, there is a vertical displacement of 0.6 meters. So the work done by this mass of 2.7 kg is by displacing it by 0.6 meters. Hence, that is the work done by the block. We'll just write here work done. First is by block. So that I will write as WB, which is equal to its weight multiplied by the displacement that it is happening. So 2.7 into 9.81 into 0.6. Okay, this is force into displacement, and it would be positive since the work is happening along the direction of that force, right? So how much is that? It comes out to be 15.8922 Newton meters. Second, when the block reaches this point B, this spring will get activated, and it will also do work, but against the block. So by spring, work done by the spring or by the resistance, what we call Ws, is in negative integration of S1 to S2, the resistive force multiplied by the ds. So what is Fr here? Fr is this stiffness is given, right? And let us say that this spring, it gets compressed by a distance of s. So let us say spring is compressed by s meters. Okay, so Fr is equal to K into S, which is equal to 876 S, right? And now we can, and what is S1? S1 is at this position, means the unstretched position, that is equal to 0, and S2 is equal to S, because that much the spring gets compressed, right? So Ws, we generally represent this by Wr, right? Resistance. Wr is negative of S1 is 0 to S. Fr will be 876 S times ds. So it is minus 876 S square by 2, 0 to S. So it's minus 876 by 2 is how much? 438, right? So minus 438 times S square. Minus 438 S square. Okay, this is the work done by the resistance. When we add both of them, that will give us the total work done. So we have work done is equal to change in the kinetic energy. So it is 15.8922 minus 438 S square is equal to half into 2.7 into, now see what is happening is it is being released from rest, hence we can say U is equal to 0, and when it slides down and the spring gets compressed by S meters, okay, this is where we need to end our numerical. Okay, we are not bothered that how much this spring is again going to push it, we only need that how much it gets compressed. So this is the end point of this block for us in this numerical, and the velocity at that point also has to be equal to 0 because it stops there, right? So V is also equal to 0, so it is half into mass into 0 square minus 0 square. Okay, so you will get S is equal to 19.048 centimeters. Let us move to next numerical. So what is given here is a 4.5 kg block is released from rest at A. So U is 0, mass is given. Determine the compression of each of the springs after the block strikes the platform and is brought momentarily to rest. Initially both springs are unstretched. Assume that the platform has a negligible mass. Okay. So there are two springs here, K1 and K2, as you can see, with their stiffness K1, K2, and there is a distance of 0.075 meters between the first and the second spring. This block is going to fall down, and let us say it falls this much distance. Okay, somewhere till here. Now this much distance I know it is 1.5. Let us say this total distance is, I would say it is S. Okay, so spring 1, okay, let us write all the data first. Mass is 4.5 kg, U is equal to 0, and you see that after this block reaches this point here, 1.5 plus S, its velocity again becomes 0, final velocity, because it is brought to momentarily rest. So V is also equal to 0, and now we just have to check what is the work done by all of them. So work done, first is by the block. By block, what is the work done? So it is WB, I will say, and the mass is acting like this, 4.5 kg, and the displacement is also happening in that same direction, therefore the work is positive. So 4.5 multiplied by 9.81 into 1.5 plus S is the total work done, right? So if I want to simplify this would be around 44.145 into 1.5 plus S. Then the second work that is done is by the spring. So I'll say by spring 1. Okay, by spring 1, and spring 1 gets compressed by how much? It gets compressed by S. Okay, so it is compressed by distance S meters, we would say. So here S1 is when it's unstretched position, S1 is equal to 0, S2 will be equal to S. Okay, S1 is 0, S2 is equal to S. So the work done by the spring WR1, I will say, is negative integration of S1 to S2, which is 0 to S, and into the resistive force Fr multiplied by ds. Fr will be, now it will be K1 into S, so it is 5300 into S times ds. So this will come out to be minus 5300 by 2 into S square, right? So it is minus 5300 by 2 into S square. Work done by spring 2. So by spring 2, and how much is this spring getting compressed? It is getting compressed by S minus 0.075. So it is getting compressed by a distance of S minus 0.075. Okay, and S1, that is its unstretched position, this is the S1 position, is 0. S2 is equal to S minus 0.075, and S2 is S minus 0.075. The work done by spring 2, I'll say WR2, is minus of integration 0 to S minus 0.075 into its stiffness is 7900 Newton meter. 7900 into S times ds. So you will get this as minus 7900 upon 2 into S minus 0.075 square. Okay, now we can add all the works that is equal to the change in kinetic energy. So work done is equal to change in the kinetic energy. Work done by block was how much? 44.145 into 1.5 plus S. 44.145 into 1.5 plus S minus 5300 by 2S square minus 7900 by 2 into S minus 0.075 the whole square is equal to half into mass is 4.5 into V square minus U square, that is going to be 0 because U is 0 and V is also 0, right? So this term becomes 0. We need to solve this equation, and after solving the equation you will get S is equal to 0.1431 meters. Therefore we can say that spring 1 deforms by 0.1431 meters, spring 2 deforms by 0.1431 minus 0.075, which is equal to 0.0681. Let us solve the next numerical. What is given in the question is determine the velocity of 27 kg block A if the two blocks are released from rest and the 18 kg block B moves 0.6 meters up the incline. The coefficient of kinetic friction between both blocks and the inclined plane is mu is 0.1. Okay. So now here they have told that this block B is moving up the incline, right? And nothing is said about block A, but definitely the block is going to move downwards. But let us not assume that. Let us say that both the blocks they move up. Okay. So first let us write the data of block A and block B. Block A we have mass, which is 27 kg, and here is block B is 18 kg. Weight will be 27 into 9.81, which is 264.87 newtons, and here it is 18 into 9.81, which is 176.58 newtons. Okay, now when we have to resolve them, see the weight will be acting like this. This is WA. Okay, this component and this component we need to know. So this is WA cos theta, which is 60, and this is WA sin theta. So this is WA sin 60, WA cos 60. So I will write here the sin component and the cos component of both. So this is sin theta cos theta. So WA into sin theta, that is W this into sin 60, is going to give me 229.384 newtons. I am just writing it in the beginning only so that later on we don't have to keep on calculating. WA, this is your WA into cos 60 is 132.435 newtons. Block B, this is acting downwards this way. This is WB. This component is WB cos 30, and this is WB sin 30. So WB sin 30 is going to give me 88.29 newtons, and WB cos 30 is going to give me 152.9227 newtons. Okay. Now let us start with our assumption. Let us assume that both of them move upwards. So let us assume both blocks move up and with their own reference. Okay, means this will move like this will move like this. Second, let us say that block A moves up by amount of delta SA. Let block A move up by delta SA, and third is let block B move up by delta SB. Okay, delta SB is given to us, it is 0.6 meters, means that much is the change which is happening, right? Okay, now we can write the equation for the lengths. So if I take this as a reference, I can say that this much is XA, this is XA, this is XB, right? So 2 times XA plus XB is going to give me L, and see this part, it remains same, it never changes. What changes is only this part, XA and XB, correct? So 2 times XA plus XB is going to give me L, right? Now after the change has happened, after block A has moved up by delta SA and after block B has moved up by delta SB, what we can say is, see, there will be a change in length. So here there is a moment of delta SA and here there is a moment of delta SB. So what will happen is 2 times XA minus 2 times delta SA plus XB minus delta SB is equal to L. You need to understand that this length never changes. This length will never change. It will always get compensated with whatever changes are happening. And see, since we have assumed both of them to be moving upwards, this equation might look absurd for now. But what we are actually finding from this equation is the relation between their movement. What is happening, whether they are actually moving up or whether one is moving down, one is moving up. Okay. So what we can say from here is 2XA plus XB minus of 2 delta SA plus delta SB is equal to L. Now this term is actually L, so both of them will get cancelled, right? So what we can understand from here is 2 times delta SA is equal to negative of delta SB. This statement here says that if B moves up, A moves down. So now we are asserted about their movements and we will take this only, this movement only. And since delta SB is moving by 0.6, delta SB is 0.6 meters, delta SA will be 0.3 meters. Now we can actually use the equation of work done is equal to change in kinetic energy. But before that, we need to understand what is the work done by A and what is the work done by B. And for that, we will draw the free body diagrams of A and B. So let us draw the free body diagram of A first to understand what is the work done by A. Here I have a tension of 2T. The weight which is acting downwards is, I have already calculated that, which is 264.87 newtons. And also its sine component and cos component we have calculated, right? 229.384 and 132.435. Now the friction is also given, it is 0.1, so mu is 0.1. We will also have to consider the normal reaction here now. So the normal reaction, let's say it is N1, and in which direction is the movement happening. So since B is moving up, A will move down, and in whichever directions they are moving, those directions they decide the sign convention for each block. Okay, so since we are taking it in the reference of the block itself, that is the reason those directions will determine the sign conventions. So if this is moving like this downwards, the frictional force will be this way, which is 0.1 times n1. I guess it's 0.1 itself, yeah, 0.1 times n1. Okay, so we can calculate from this. N1 we can calculate first. Summation Fy equals to 0. This will give me N1 is equal to 132.435 newtons, and therefore F mu, that is the frictional force, is 0.1 times this, which is 13.2435 newtons. Okay, this is done. Now summation Fx equals to 0. No, summation Fx is basically the one which is causing the work. So, and the displacement of A is how much? Delta SA is 0.3, right? 0.3 meters. So the work done, summation Fx is equal to how much? This is the positive direction like this. So it is 229.384 minus 2t minus 13.2435. This is summation Fx, and therefore the work done by A, work done by A is equal to 229.384 minus 2t minus 13.2435 multiplied by 0.3. Okay, similarly we will find the work done by B, block B. So the FBD of block B, that we have to first determine. FBD of block B, let me draw the block. So the weight of the block is 176.58 newtons. There is one tension that is acting in this direction like this. This is T. The movement is happening in this direction, so that is positive. And it is happening by delta SB, which is equal to 0.6 meters. The resolution of this weight is 88.29 and 152.9227. So 88.29 and 152.9227, I guess. I hope it's correct. Okay, and the frictional force, for which we need the normal reaction. So the normal reaction would be like this, N2 I'll say, and since the direction is this way, the frictional force would be like this, which is 0.1 times N2. So now summation Fy equals to 0 will give me N2 is equal to 152.9227 newtons. F mu, that is the frictional force, will be 15.29227 newtons. Okay, summation Fx, which is actually causing the motion, is, since this is the positive direction, therefore T minus 88.29 minus 15.2923. Okay, and the work done by B is T minus 88.29 minus 15.2923 multiplied by 0.6. Yeah. So we have got work done by A and work done by B. We can add them up. So 229.384 minus 2T, 229.384, or rather I'll just copy that thing. That would be easier. Right, and plus the work done by B, which is this one. So this is the total work done. Right, this is the total work done. Anything else which is doing the work, there is no resistance here, right? So only these two blocks are doing the work. This is equal to change in kinetic energy. So half into, first I'll write for block A. A is how much? M is to 27 kg. So half into its mass 27 into VA square. Right? There will be VA square minus 0 square. Okay, this is for block A, kinetic energy, plus half into 18 kg was the mass of block B into VB square minus 0 square, because both are starting from rest. So let us solve this equation. Let's see what we get. 229 multiplied by 0.3, 68.27 minus 0.3 into 2, which is minus 0.6 T, minus 13.2435 into 0.3 is minus 3.97305 plus 0.6 times T, and minus 88.29 into 0.6 is minus 52.974 minus 15.2923 into 0.6 is minus 9.17538. It is equal to 13.5 VA square plus 9 times VB square. Okay, this will get cancelled. So what we get here is 68.27 minus 3.97305 minus 52.974 minus 9.17538 is, this is equal to 2.14757. Okay, so after getting this equation, now VA and VB, can we have a relation between VA and VB? We'll take the help of this displacement equation. So if I differentiate this with respect to time, what I will get is 2 times VA plus VB equals to 0. Therefore 2VA, or rather VB I can write as minus 2VA. Correct. So VB is minus 2VA. I can substitute here. So it will be 13.5 times VA square plus 9 into minus 2VA square is equal to 2.14757. So you will get VA as equal to 0.20829 meters per second, and VB you will get as 0.41658 meters per second. Let us solve next numerical. Okay, so what is given in this question is we need to determine the height h of the incline at this position D, to which the 200 kg roller coaster car will reach if it is launched at B with a speed just sufficient for it to round the top of the loop at C without leaving the track. The radius of curvature at C is rho C is 25 meters. So we need to find the velocity at this point first. Okay, and to find the velocity at this point, the condition that is given to us is that this car goes around this loop and the velocity by which it is launched here is just sufficient for it to round the top. Now, since it is traversing a circular track, there are centripetal accelerations that would be there, and there is this gravity also is there. At this topmost point, the gravity is acting downwards. Okay, so there is this force due to gravity, and there is also this upward force, centrifugal force is there. I'll say it is Fc. So when this Fc and Fg, they both are equal, that is the just enough condition for that car to stay at that position. I mean to not fall from that position, right? So let us see what is given to us. M is 200 kg and the radius of the track is rho c is 25 meters. For the car to just stay, or for the car to just round the top, it is Fg has to be equal to Fc. The gravitational force should be equal to centrifugal force. Gravitational force is nothing but m into g, and this is equal to m into the acceleration, and here we will be using the centripetal acceleration, because see, centrifugal force is nothing but it is equal to centripetal force, just opposite in the direction. So it is v square by rho. This is the centripetal acceleration. M gets cancelled, so 9.81 is equal to v square by rho is 25. Therefore v is equal to 15.6605 meters per second. So this is the velocity v that we need at this point. V is 15.6605 meters per second. Still we do not know what is the velocity at this point. I'll say it is u equals to something. So now here what we'll do is we will apply our work energy principle. So the weight is acting downwards, which is 200 into 9.81, and since this car from point B it is going to point C, the displacement is happening in the upward direction. So the work that is done by this weight is negative, correct? Because the weight is acting downwards but the displacement is happening upwards. So it's a negative work that is being done by the weight. Therefore, work done is change in the kinetic energy. Therefore, minus of 200 into 9.81 into 35 meters, the displacement, is equal to, now here we are applying work energy between B and C. Okay, so minus 200 into 9.81 into 35 is equal to half into mass is 200 into final velocity is 15.6605 square minus the initial velocity. So from this we can get the initial velocity. U will come out to be equal to 30.5279 meters per second. So this is the velocity by which the car has to be launched, this roller coaster has to be launched. Okay, fine, we got this. Now we need to find that how much more it will go till this point D. So what we can do, we can apply the work energy between B and between D, and the work done by this weight in that case would be minus 200 into 9.81 into h, because now it is rising by h, the displacement is happening in the, still it is happening in the vertical direction only. So applying work energy between B and D. So it is minus 200 into 9.81 into H is equal to half into 200 into, so we know the initial velocity now, it is 30.5279. We do not know, or rather we know actually the final velocity also, because here it is said that we need to determine how much it will reach here, right? So it means that after reaching at this point D, the roller coaster stops. So V here will be equal to 0 basically. So 0 square minus 30.5279 square. So you will get H is equal to 47.5 meters. So that's it about the work energy principle.